The human skeletal system is built to allow us to stand upright, but it is up to different anatomical systems to keep us balanced and prevent us from falling over as we change our body's position. In order to balance, we need to see clearly when moving, orient oneself with respect to gravity, and determine the direction and speed of movement. The ear is particularly critical in maintaining balance by telling our brains where we are and whether or not we are moving. The ear is split up into 3 regions: the external ear, the middle ear, and the internal ear. The internal ear houses 3 major structures: the cochlea, which conducts sound waves and allows hearing, and the semicircular canals and vestibule, which are responsible for equilibrium. The semicircular canals consists of 3 endolymph-filled ducts, each positioned on a different plane. The posterior duct is stimulated by moving your head side to side. The anterior duct responds to nodding your head yes. The lateral semicircular duct is stimulated by the motion of shaking your head no. Together, the semicircular canals detect and inform the brain of the position of your heavy head. Each canal has a bulge at the bottom called the ampulla. The ampulla is a swelling of the membranous labyrinth that communicates with the vestibule. Each holds the cristae ampullaris, which is the sensory organ of the structure, consisting of hair cells and supporting cells. Each cristae is bound to a cupula, which is a flexible, elastic, and gelatinous structure that extends the full width of the ampulla. Continuous with the semicircular canals is the vestibule. The vestibule is made up of 2 chambers, also filled with endolymph, called the saccule and the utricle. Both have maculae, which are the receptors of the vestibule, and consist of bundles of hair cells that respond to fluctuations between movement and staying still. The maculae are covered in a gelatinous layer. On top of the gel are otoliths, which are calcium carbonate crystals that add weight to the top of the gel. The semicircular canals and the vestibule relay the information collected by the receptors to the brain. Here, information from other systems, such as the eyes, is integrated and then distributed to allow the rest of the body to make postural adjustments in order to keep our center of gravity over the base of its support.
Inertia and Newton's first law of motion. Inertia is a property of matter that causes it to resist changes in velocity. Newton's first law, also known as the law of inertia, states that if a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at a constant speed unless a force acts upon it. This means that objects cannot start, stop, or change direction all by themselves. The amount of inertia that an object possesses is proportional to its mass. However, inertia is not the same thing as mass or momentum. Inertia is useful in navigation systems because massive objects can provide a constant reference for acceleration and changes in direction because they maintain a constant orientation in space. Equilibrium and homeostatic regulation. A mechanical body is said to be in equilibrium if it experiences neither linear acceleration nor angular acceleration. Unless an outside force disturbs it, it will continue in that condition indefinitely. Changes in temperature, pressure, the addition of more reactants, and changes in other variables cause a system to create a new point of equilibrium. Dynamic equilibrium is the steady state of a reversible reaction where the rate of the forward reaction is the same as the reaction rate in the backward direction. Any system in dynamic equilibrium tends to reach a steady state, which is a balance that resists outside forces of change. When such a system is disturbed, built-in regulatory devices respond to the departures to establish a new balance. This process is known as feedback control. All processes of integration and coordination, whether governed by electrical circuits or by nervous and hormonal systems, are examples of homeostatic regulation. Static equilibrium, also known as mechanical equilibrium, means the reaction has stopped. In other words, the system is at rest. In biology, the equilibrium of a system is called homeostasis.
So why exactly does spinning make you dizzy? Inertia and gravity each play a role in this. Inside of your inner ear, there are the 3 semicircular canals arranged at right angles to one another, just like a gyroscope. These are responsible for dynamic equilibrium and rotational acceleration. Each one senses movement on a different axis, and together they orient your 3-dimensional space. Inside of these canals there are tiny hairs and a fluid which moves around as you move your head. It's these hairs that sense movement and send a signal to your brain regarding position. As the liquid moves, it disrupts these tiny hairs, moving them back and forth. When you start spinning in one direction, the fluid in your ear moves the opposite direction, disrupting the tiny hairs and sending a signal to the brain. After a few seconds of this, the hairs start to resist the movement and become stabilized. Therefore, your perception of spinning has become normal. When you stop spinning because of inertia, the fluid in your semicircular canals stays persistent. This is why you have the sensation of spinning still when you're actually stationary. That was an example of dynamic equilibrium at work. There's also a static equilibrium system called the vestibule, which is responsible for linear movement. The receptors of the vestibule are called maculae, and they also consist of bundles of hair cells that respond to fluctuations in movement. Much like in the semicircular canals, these receptors are covered in a layer of a gelatin-like substance. On top of that layer sits otoliths, which are just tiny crystals made up of calcium. When the head changes position, it's gravity that pulls on the gelatinous layer, which then triggers the maculae and signals a balance response to the brain. During linear acceleration, such as when riding in an accelerating car, inertia causes the mass of the otoliths to lag behind the movement of the head, which causes the hair cells to bend. This mechanism tells your brain that you're moving forward. The otoliths that sit on top do so because they are less dense than the fluid they're mixed with. This can cause problems because if these crystals come in contact with the tiny hairs or get wedged within one of your canals, it can confuse your brain, making you dizzy. This is one of the causes of vertigo.
Have you ever had too much to drink and got the spins? This happens because alcohol has the ability to affect a person's balance. Normally, blood that enters the inner ear has the same density as the endolymphatic fluid that is normally contained within the inner ear compartments. The main sensory organ of the inner ear, called the cupula, is responsible for spatial orientation by informing the brain when a head movement has occurred. With a normally functioning inner ear, the cupula is stimulated only when it is pushed by the surrounding endolymphatic fluid when the body moves. However, this delicate balance between the cupula and endolymphatic fluid is altered when alcohol is present. When alcohol enters the bloodstream, it makes the blood less dense. When the alcohol-infused blood enters the inner ear, the alcohol rapidly diffuses into the inner ear cupula because of the proximity of the structure to blood capillaries. This blood-alcohol mixture messes up the delicate balance between cupula and endolymphatic fluid, causing you to have the spins. Another interesting fact is spatial disorientation. Spatial disorientation is the inability of a person to correctly determine their body position within space. This phenomenon refers especially to aircraft pilots and underwater divers. In aviation, the term means the inability to correctly interpret aircraft altitude and airspeed in relation to the ground or point of reference. This occurs when a reference point like the horizon has been lost. When a pilot cannot see a distinct visual horizon, the drift of inner ear fluid continues uncorrected. Errors in this rate of turn about an axis can build up to a rate of 0.2 to 0.3 degrees per second. If the pilot is not proficient in the use of a gyroscopic flight instrument, these errors will build up to a point that the pilot loses control of the aircraft, usually in a steep diving turn known as a graveyard spiral. During the entire time leading up to the graveyard spiral, the pilot remains unaware that he is turning, believing that he is maintaining a straight flight path.